Okay, this is John Perham here, and I'm going to now present the solutions to the first test problems in MATH1231 algebra. Get rid of these, we won't need them. Let's start with the yellow problems, and so this is the first one. So we've got this set S, which is consists of some vectors in R4 such that the x1 is equal to x4 and x2 is equal to minus x3. So we can establish the components of a member of S using this. So x1 is replaced by x4 and x2 is that. So for any values of x2 or x3 and x4, that's a member of S, and we can view that as a column vector using that. So the result of setting x3 and x4 equal to 0 can be seen using that to be the 0 vector, so that the set S is not empty. So we can establish a second member of S using this. So we replace x by y, and we can see that using that. So we can see the result of adding these two vectors using that, and it's pretty easy to see that that is also a member of S, because we just have to replace x4 by x4 plus y4 in all this. And finally, we can see the result of multiplying our vector x by some scalar k, and we can see that that is clearly also a vector in S. So the set S is not empty and is closed under addition and scalar multiplication. So that's all the conditions for the subspace theorem are satisfied. So let's go on to problem 2. So we've got these three polynomials, p1 of x, p2 of x, and p3 of x. And we're asked, is the polynomial q of x, given by this, in their span? So we better establish them. So if q of x is in their span, then we can find non-trivial values of the parameters a, b, and c, such that the polynomial given by the a times the first p plus b times the second one plus c times the third one minus q should be the 0 polynomial. So let's do that, and that will be the case if the coefficients of all the powers of x in this expression here are 0. So we can collect those. So we look at the power of x to the power j in this polynomial for j equals 0, 1, and 2, and collect those. And we can see, and these have to be 0, so we can see that these are three linear equations for a, b, and c. So let's try and solve those. So we first calculate the coefficient matrix, which is the coefficient of the jth variable or parameter in the ith equation. So there it is, and we can visualize that as a matrix. And to get the right-hand side vector, we multiply this coefficient matrix by the parameters and subtract off the equations. And we can visualize that as a column matrix using that. Well, we've now got a set of linear equations, so we form the augmented matrix by joining each row of the coefficient matrix to the corresponding element of the right-hand side vector, which we can do using this, and we can see it as a matrix like so. And we now apply our method of row reduction, so we can see we add twice the first row to the second and subtract 4 times the first row from the third, and we can do that using this. And look at the result. That's a matrix using this, and we can see that indeed we've got zeros under the diagonal in the first column. And now we do the second phase, and we add 3 times the second row to the third row. So the first row stays the same, the second row stays the same, and the third row is the result of this addition here. And we look at that in matrix form using that, and we can see that the linear equation associated with the third row, which is the equation 0 equals 6, has no solution, so that therefore q of x is not in the span of the other 3 polynomials. Okay, let's go on to problem 3. This is pretty quick. A set of 7 vectors in R7 may be a basis for R7. Is that true or false? The answer is true, since if we have 7 linearly independent vectors in R7, they will form a basis for it. Statement B is false, because if some of the vectors are linearly dependent, then they cannot form a basis for R7. So that was pretty fast. And then problem 4, we have a linear transformation from R2 onto R3. So it's the function, or call it a function, t applied to this element is this value here, and t applied to this one is this one here, and t applied to the vector 2, 5 is this one here, and show that t is not a linear transformation. Well, if it was a linear transformation, then t25 should be equal to twice of t of 1 and 0 plus 5 of t and 0 and 1. And we can work that out. That's 2 times this guy here plus 5 times this guy here. And if we do the arithmetic, 2 3s is 6, minus 5 is 1, 2 times negative 5 is negative 10, plus 15 is 5, and 2 times 2 plus 5 is 9. And this will be a linear transformation if t of 2, 5 is equal to this, but it's not. So t is not a linear transformation. So that was the end of the yellow problem. So let's go to the green problems. There's several. So we start with question 1. So we've got a set of vectors x in R2, and their components are such that the product of x1 and x2 has to be less than or equal to 1. So show that that is not a subspace of R2. Well, we can form one of these vectors and visualize it as a column vector using this. And the result of setting x1 and x2 equal to 0, which clearly satisfies this, we can see that to be the 0 vector. So at least this set is not empty. And we can establish a second member of the set using this, which we can visualize. And now we look at their sum. Which we can visualize like that. So this will be a member of the set if the product of this and this is also less than or equal to 1. So this product is this. And we can see that this is not always the case, because if we choose x1, y1, x2, y2 to be 1, then the value of this is 4, which is not less than or equal to 1. So this is not a subspace of R2. Problem 2, so we consider 3 vectors, or 4 vectors, v1, v2, v3, and b, and we can establish those using that and visualize it. So this is the first one, v1, the second one likewise, and the third one likewise. And the vector b is established using that, and we can see that it's the right kind of shape. Well, the question is, find, if any, the conditions on the components of b such that it is in the span of the first 3 vectors. Well, that will be the case if we can find values of 3 parameters, alpha, beta, and gamma, which we can establish here, such that if we take a linear combination of the 3 vectors and subtract off the vector b, then the result, which we can do using this, then the result is, see it doing this, then that should be the 0 vector. Well, we can see that that is a set of 4 linear equations for the 3 parameters alpha, beta, gamma. So we can dig out their coefficients in the usual way. We look at the coefficient, say, of the second variable in the first equation, and we can do that for all the equations, and we get this coefficient matrix. And now we want to, which we can look at like so. So it's a 4 by 3 matrix, 4 rows and 3 columns. And we can find the right-hand side vector by multiplying the coefficient matrix by the parameters and subtracting off the vector. And we can look at it using that, and not surprisingly, it is equal to the vector b. So we can construct the augmented matrix using this by joining up for each row of the coefficient matrix, we add the corresponding element of the right-hand side vector, and we can look at that as a matrix using this. And now what we want to do is to carry out the row reduction here. So we subtract twice the first row from the second, the first row from the third, and we add the first row to the fourth row. So we can do that using all this here, and look at the result, and we can see that indeed we have got zeros all down the subdiagonal elements of the first column. And now we go to the next phase, which is we subtract the second row from the third and add twice the second row to the fourth row. So there we go, the first 2 rows are unchanged, and we perform those operations, and we get this, and we can look at that as a matrix using that. Well, that's quite interesting, because we can see that this row is non-leading, and so is this one. Oh, sorry, this column is non-leading, and now we want to. So there's no unique solution. However, there will only be a solution if this is equal to 0 and this is equal to 0. So we see that a solution only exists if the 3, 4 and 4, 4 elements vanish. Well, we can dig those elements out, and there they are. And we can see that the first one involves B1 and B1, B2 and B3, and the third involves B1, B2 and B4. So it's convenient to set these equal to 0 and solve the first for B3 and the second for B4. We can do that all at one go using this. And so B is in the span of the first 3 vectors if it is of the form this. So we put those solutions into our vector B, and we can see for any values of B1 and B2, this is a solution, or is such that B is in the span of the 3 vectors. Now on to problem 3. So we have 3 vectors v1, v2 and v3, which we can establish using this and view like so, and then the second one and view it like so, and the third one and view it like so. And there are 2 parts to the question. Find the values of these parameters here, which not all 0, so we can establish these parameters using this, such that the linear combination here is the 0 vector. In other words, if that's the case, then the 3 vectors will be linearly dependent. And then the second part of the problem is determine, giving reasons, whether or not there is a linear map T from R3 to R2 such that T applied to the first function, or the first vector v1 is this one, and T of v2 is this one, and T of v3 is equal to this one. So let's do the first part first, always a good idea. So we can establish this linear combination of the 3 vectors using that, and we can view that as a column vector using that, and that has to be the 0 vector. So these are a set of homogeneous linear equations for the parameters alpha 1, alpha 2, alpha 3, and we can find the coefficient matrix using this. And there it is. And the right-hand side vector we can find by multiplying the coefficient matrix by the parameters and subtracting off the vector. That should be the 0 vector, which it is. And now we have this augmented matrix. There it is. And we can look at it like so. The first stage of the row reduction we can carry out. We can subtract the first row, twice the first row from the second, to get a 0 here, and add the first row to the third. So we do that. And there it is as a matrix, and we can see that that is indeed the case. And now the second stage of the row reduction is we just subtract the second row from the third, leaving the first 2 unchanged, and of course that will give us a bunch of zeros in the last row, which we can see using this. So we can see that the linear equation associated with this row is 0 equals 0, so it's automatically satisfied, and we can dig out the linear equation satisfied by the second row by multiplying it by, or taking the scalar product of it with the parameters and the element 0, and That's an equation for alpha involving alpha 2 and alpha 3. That has to be 0, and so we can set that equal to 0 and solve it, say, for alpha 2, giving that. And the linear equation associated with the first row can be seen by taking the first row, taking the scalar product with this vector here, and applying the solution for alpha 2, and that gives us that, and we can set that equal to 0 and solve it for alpha 1 equals that, and we can now apply those two solutions to the parameters, and we can see that they will be a solution for any value of alpha, a non-trivial solution for any non-trivial value of alpha 3. Alternatively, we could say that V3 is equal to minus 7V1 plus 3V2. The values of t applied to the three vectors can be entered as the columns of a matrix by entering them as the rows here, and then taking the transpose. So let's do that, and we can visualize that as a matrix using that. And we see indeed that each column of this matrix is the appropriate vector. So if this is a linear map, then we will require that t of v3 should be equal to minus 7 times t of v1 plus 3 times t of v2. We can calculate that by taking the scalar product of the matrix T with the columns with the parameters, and that should be the 0 vector, but it's not. So therefore T is not a linear map. Okay, so we'll stop there.